All right, so this is question, I think, 4 from 8.4. Says the diameters in inches of 17 randomly selected bolts produced by a machine are listed using 95% confidence level to construct a confidence interval for the population population variance sigma squared in the population standard deviation sigma and interpret the results. Okay, so what we're looking at here, if you remember from 8.4, okay, our formula for variance, okay, is this thing right here. Okay, so we'll write that down first. So you go n minus 1 times s squared, or sigma squared, or if we want to refer to it as just the variance, that's fine, divided then by your chi-squared. Okay, now this is going to be the chi-squared right value. It doesn't matter though, it's just the chi-squared that we get back that is biggest. Okay, that's going to be less than sigma squared, which is what we're trying to estimate here. Okay, our variance. And then n minus 1 s squared over chi-squared left. Okay, you got to remember that degrees of freedom is equal to n minus 1 in this case. Okay, so what would n be in our situation? N is 17, so degrees of freedom 16, right? Okay, so I'm just going to start plugging stuff into this confidence interval. Okay, n minus 1, we've got that, 16. Now we've got to find s squared, which s is standard deviation, and if you square standard deviation, you get variance. So however you want to look at that, we've got to find one of those two things. Okay, now they don't tell me that information, correct? Okay, they give me this table of values. So what we have to do then is process that data, and I think the best way of doing that is to use Excel. Okay, especially in this situation, because if you are a Desmos person, you can find standard deviation with Desmos by typing in a table. However, with Desmos, you're going to be hard-pressed to find the chi-squared values. Okay, so if you're a Desmos person, to find your chi-squared values, you'd probably have to either turn to the table or to Excel. If I'm going to turn to Excel, I might as well just do everything in Excel. Okay, so I'm going to type these data values in column A, so just give me a moment to do that. Yes. Does it? It'll paste them in then? Okay, so let me see. Okay, so this, you're saying this box right here. So, like, I've already closed down my my assignment, so I can't copy it right now. But you get that, it'll copy it, and you can just paste that straight into A. Awesome. Everybody understand that? Cool. Okay, so I've typed those in. Now we're going to I'm just going to zoom in on just this selection. I know my data is in column A, so I can put two things here. I can either type in standard deviation and get that value and then square it, or if I actually type in var.s, okay, that's going to give me the variance of that list. Okay. Let's see here. Let's make sure I did it right. Estimates variance based on sample, ignores logical values and text in the sample. Okay, so 8A. Okay, so there's my variance. Or you can go, like I said, you go stdev.s, type that in, I get that number, but if I square that number, square B2, I'm going to do it that way. Does it give me back to what the variance said was? Does that kind of make sense to everybody? Okay. Now it says round to 3 decimal places as needed. So if you are struggling with, you think you've done everything correctly, but you're getting the question wrong, there you go. It might be because you rounded to like 4 decimal places in this value, and then the rounding error creates issues. So I'm just going to make sure that I round this out far enough. I use I'm going to go out to probably like this 7 right here. So then I know that this 6 here is not going to be impacted by rounding errors. Does that make sense? Okay. So that's going to go right here, 0.0. 0.07697. Okay, now, just be cautious. That was the variance. Okay, so I don't need to square it now because the variance is already squared. Does that make sense? Okay, if you use the 0.277 number here, you would then have to put that exponent of 2 there and actually square that quantity on your calculator. Okay, just know that relationship between standard deviation and variance. Now I got to find chi-squared left and chi-squared right. Okay, so I think the best thing to do, so chi-squared left and right, there's actually, I think the way I've shown you for the chi-square is to go chi-squared dot, okay, so I'm going to go chi-square dot inv, okay. Now, it is left-tailed cumulative in regards to how it is going to spit back information to me, okay. So, if we look at it, it says returns the inverse, I'm reading this right here, it says returns the inverse of the left-tailed probability of the chi-square distribution. Now, if I hit parentheses, it tells me what it's going to ask me for. It's asking me for the probability, okay? Well, that probability is alpha over 2. Does that make sense to everybody? Okay? So, just helping me remind myself, right here, we go alpha over 2, and then it'll ask me for degrees of freedom, okay? That will give me one of my chi-squared values. Okay, so we wanted a 95% confidence interval, so alpha would be 0.05, alpha over 2 is 0.025. And my degrees of freedom we said was 16, and that is the chi-squared left value that we're looking for. So our chi-squared is a right-skewed distribution, and what we just found, okay, is that area right there, okay? Is that okay with everybody? That like I said, I didn't find that area, but that area is 0.025. That's half of alpha. And the chi-squared value that segments that area, breaks that area off there, and then we'll have another area over here, 0.025. So it creates this 95% area here in the middle. That value right there is the 6.907 number. Is that okay with everybody? Okay. Now, I need to find this. So I know that that area is 0.025 on the right-hand side. I also need to find, let's see here. I also need to find that chi-squared value right there. Okay. Now, you can do it two ways. If you're going to use this here, then you need to make sure that you understand that that is dealing with, that is a left tailed distribution, okay, cumulative. So I would need to type in, if I want to use this, I need to type in what all of this yellow area here would be. Does that make sense? Okay. So you can type in equals chi-square.inv, okay. That yellow area would now be essentially 1 minus 0.025, right? Okay. So 0.975. Or you can view it as alpha over 2 plus your confidence level, so 0.025 plus 0.95, which still gives me 0.975, right? And then follow up by your degrees of freedom, okay? You can do that. If you're not a person that wants to do that addition, there's actually built in a right-tailed probability for the chi-square inverse. Okay, so when I type this in, it says it returns the inverse of the right-tailed probability of the chi-square distribution. So what's going to do is I'm going to type in this 0.025 of the right tail, and it's going to find that chi-squared value for me. Okay, so when I do this, all I got to do is type in the 0.025. So this is where the reason maybe you would like this is because that command, okay, the arguments for that command are exactly the same as the arguments that we used up here in this command. Does that make sense? Okay, and the only thing that would be different from this line and this line is the .rt. Okay, hit enter, and I get that value. Okay, that's the chi-squared right value. You can see if I would have done it differently, if I would have done chi-squared .inv and done 0.975, comma 16, is it the same 28 number? Okay, so I'm going to grab those two values, 6.9 and 28.8. Which one should go here? The 28 one. Okay, that quotient needs to be the smallest value. So in order to gain that, I need the largest denominator. So this value is going to be 28.8. I'm just going to go 454. Okay, 454. And then this one needs to be the 6.90, I'll say 77. I'm just going out long enough, far enough, because it wants it to the third decimal place, so I need to make sure that these are large enough, okay? And I may not have gone far enough. Might even want to go one more decimal place here. Is that okay? So once you then have that information, you can use, I'm just going to use Desmos real quick, or not Desmos, continue using Excel here. I just hit, if you want to use Excel as a calculator, you still have to hit the equal sign for it to calculate things. So I'm going to go 16.07697, and then we're going to divide that by 28.8454. And it doesn't know, so when I do it that way, it doesn't understand implied multiplication. So I got implied multiplication right here, correct? Okay. It actually needs me to tell it multiply. Okay, that's the one thing that might be a hiccup if you're using this as a calculator. Hit enter, gives me that value. Okay, so that is this amount right there. And then, I'm trying to cheat here. All I did is I cut and pasted what was in that because all I need to do then is change the denominator here to the 6.9077 value. Hit enter, and there's my right-hand side. So my interval for my variance, would be that. Okay, so all right, everybody. How do I then get the interval for standard deviation? I square root those two numbers. Okay, so I'm just going to hit equals SQRT of that thing right there, so B7. So there is the square root of that number. Equals then, I'll take square root of that one as well. And now that will be the interval for my standard deviation. Does that make sense? Okay. Now, as we interpret the results, I think the way, there's a lot of different ways you can interpret them, what they're going to ask you about when they say interpret the results. Basically, what we want here, if I'm a manufacturer, okay, and this is the additive characteristics or content ideas that are, I think, often more important than being able to calculate these things. We want that variance, that standard deviation, that interval. If I'm the manufacturer, from the manufacturer's perspective, we want that to be as narrow as possible. Does that make sense? Because if that interval, remember what we're doing here, we're trying to determine, so what was this, the diameters of diameters of 17 bolts. Okay? Well, if I'm manufacturing bolts, I want to make sure that there's very, very, very little variance or standard deviation from each bolt to the next. Does that make sense? Because my bolts are going to go get bought by other companies to assemble their products, right? Okay? And they're going to buy maybe washers and nuts from other companies, and my bolts need to be compatible with those other parts, right? Okay? And if, a company buys 1,000 bolts from me and they buy 1,000 nuts from somebody else and they're incompatible, we just wasted those people's money. Okay? And I probably lost the customer. So what we want to make sure happens is that the variance and standard deviation is as narrow as possible, because that will then tell me that each of those 17 in the sample, which then are a model of my population, which will tell me my population is as alike as possible. Does that make sense? So that the first bolt is almost identical to the second bolt, which is almost identical to the third, which means then that no matter where that bolt goes, it's going to work. It's going to fit in conjunction with other parts from other manufacturers. Does that make sense? Okay, and that's what I think is most important for us to understand in regards to working with chi-square distributions. We want variances in standard deviation intervals to be very narrow. Okay, if they're not, okay, and what will happen is, so they'll have all this preliminary data that they've collected over the years, and they understand through the the theoretical sizes that they want. There's a tolerance that is okay. Does it make sense? There's a standard deviation. There's a variance that they are okay with because it's so minute that even though it's not the same as the previous one, every nut is still going to fit onto that bolt. Does that make sense? And it's going to do its job. So as long as, if I'm the manufacturer, as long as my variance and standard deviation interval here that I recognize is inside that already pre-established interval, then my machines are working fine and I can keep producing them. If I am outside that interval, then we got to shut down production. We got to fix things. Does that make sense? Okay. So that's just something to think about on that side of the statistics. Does that help with that question? Okay. Are the other ones are pretty much the same, aren't they? So this is a 90% confidence interval. So when we're doing these things, the reason they give us the confidence interval, so usually when we do the confidence interval, we did it for like p hat, we did it for the mean, all that kind of stuff. We needed the confidence interval to tell us what our z-score was, right? Okay. Well, here it's a chi-squared, so it's not normal. So what we're looking for here, the only reason they give me that is so we can find our alpha over 2. Okay. So alpha over 2 here, that you would type in the command on Excel would be 5%, 0.05. Okay. All right. I want to get into one more example of the difference in means and difference in two sample means. But if you have more questions on the chi-square, we can talk about that again tomorrow as well. Okay. Yesterday, I think we finished yesterday with this one that talked about, again, we're talking about the shear strength of bolts. And we found out this value here. And I just want to make sure that we reiterate what we were discussing yesterday when the bell rang. Okay. Right now, what we're saying is that the difference in the means between these two populations, okay, is we're 95% confidence that it is between negative 3.35 and negative 2.45. Now, I don't know what the units are for shear strength, okay, for bolts, okay, but whatever those units are. Does that kind of make sense? Okay, which tells us that there is, basically they're both negative, because it's telling me basically here that mu sub 1, that population, and we'll see the math here in a minute, I believe that population is going to be the smaller population. Does that make sense? Or the lesser shear strength size. Okay? So they are more fragile, if you want to view it that way. Does that kind of make sense? Okay? If they were both positive, it would mean that mu sub 1, that population, was the one that was stronger. So don't really worry too much about right now in regards to these values. Like I said, I don't know what the units are, so they might not make any sense to us at all. Okay? But what would or should make sense to us, and we'll see in the next problem we use fish as the unit, so that'll make sense to us. Here, what we need to understand is that if this is negative, and this value here is negative, what does this have to be? Has to be negative, because this is an unknown number somewhere between those two, right? We're 95% confident then that when I say mu1 minus mu2, that quantity should be a negative number. So I'm going to write it that way. That's how I can express that as a negative number. Well, if I add mu sub 2 to both sides, I get that conclusion right there, correct? And in words, what that tells me is that population 1, its mean, okay, is less than the mean of population 2. Does that make sense to everybody? There is, which basically tells me there is a difference between the two samples. Okay? There is a difference then between the two populations. Is it okay with everybody? All right. No. So let's do this. Let's say, so that's a good question, because in your homework they're going to ask you these types of questions. Okay. Let's say that we had like a positive number less than mu1 minus mu2 less than another positive number. Okay? Well, if mu1 minus mu2 is between two positive numbers, what does this mean? What does that mean mu1 minus mu2 has to be? It has to be bigger than 0. So then, when I add mu2 to both sides, here we see population 1 has actually got a larger mean than population 2. Okay, so when 1 is positive and 1 is negative, and it could be, you know, the first one, actually, yeah, you can't do it. This one would have to be negative. So if we go negative, less than mu1 minus mu2, less than that positive value, okay? Now, that means that that could be negative or that could be positive, right? But what's the transition between negative numbers and positive numbers? 0. Okay, so if let's say that I'm working on a 95% confidence level here, I'm basically saying in this situation, when that's a negative value and that's a positive value, I'm saying that that could be a possibility. Does that make sense? I'm not saying that I'm 95% confident that mu1 minus mu2 is equal to 0, but I'm saying mu1 minus mu2 is or could be equal to 0. And if I do that, I would get that, right? So I'm saying if my interval includes 0, statistically speaking, we are saying then there is a chance that there is no difference between the two populations. Does that make sense to everybody? Okay? Because mu1 minus mu2 could be 0. Okay? So basically what that's saying then is that we're not getting enough of a difference in the interval, okay, to make an argument that one population is bigger or smaller than the other. Okay? So if I was doing that with, let's say, our scores in this class compared to 7th period, okay, if I found the left interval to be negative and the right interval to be positive, I would say, statistically speaking, there's really no difference in the two courses. Okay? Does that make sense? The next question, so that is, as you answer your questions in your homework, they will kind of target a little bit of that. Okay, now you only get, there's only 5 questions in your homework over these confidence intervals. There's one question in the assignment that deals with, I think it's just a simple like vocabulary question, because I took these 5 questions from a different textbook, and the way Math Excel works is I can use 20 questions from other textbooks, but to make an assignment, I have to use 1 question from our textbook. Our textbook doesn't have this section in it all by itself. And what I mean by that is this concept, this confidence interval in our textbook is coupled with hypothesis testing. So if I wanted to give you a question of this stuff from our textbook, not only does it ask this, but then it asks you to go further with hypothesis testing with it, and we don't know that stuff yet. Does that make sense? So I didn't want to give you those questions. Most textbooks are that way. So I scoured like 15 different textbooks on Math Excel, and I was able to come up with 5 that are just working on these confidence intervals and nothing about hypothesis testing. Okay?
So when it talks about the negative and positive ones, is there not enough information? Is that what you're saying?
No, it just means that the sample that was chosen demonstrates that there is no difference between the two means of the populations. Another sample might show something different. Okay, but this sample, we're 95% confident that there's no difference between the two populations that the samples came from.
So they're just the same?
We would argue that, I don't want to say that the populations are the same. I would argue that their means are the same, because that's the statistic or the parameter that we're trying to estimate. This one says, in the summer of 1988, Yellowstone National Park had some major fires that destroyed large tracts of old timber. I don't know what that word, why bear is in there. Near many famous trout streams. Fishermen were concerned about the long-term effects of the fire on these streams. However, biologists claim that the new meadows that would spring up under the dead trees would produce a lot more insects, which would in turn mean better fishing in the years ahead. So Guide Services registered with the park provided data about the daily catch for the fishermen over many years. So ranger checks on the stream also provided data about the daily number of fish caught. So Yellowstone Today, which is a park publication, indicated the biologist's claims were correct, that the daily average catch increased. Okay, This is like a legitimate study that was done. So suppose you are a biologist studying fishing data from Yellowstone National Park streams before and after the fire. So fishing reports include the number of trout caught per day per fisherman. A random sample of 167 reports from the period before the fire showed that the average catch was 5.2 trout per day. Assume that the standard deviation of daily catch, I don't know why it says cater, per fisherman during the period was 1.9, and that's the population standard deviation. Says another random sample of 125 fishing reports 5 years after the fire showed that the average catch per day was 6.8. Okay, so assume that the standard deviation during that period was 2.3. Compute a 95% confidence interval for the difference of population means. So the question is, if we're looking at just the average catch per day, 5.2 to 6.8, somebody might argue, yes, there's better fishing, but those are point estimates. Does that make sense? Okay, and with the standard deviation, look at the standard deviation. This is 2.3, and this is 1.9. So if I add 1.9 to that, and I subtract 2.3 from that, we're now kind of putting those numbers very close to one another. Does that make sense? And that's what the standard deviation kind of allows us to do. So even though this is greater, there's some overlap with this information. So I want to make sure through statistical testing that I can argue that fishing is better or it is not better. Okay, so this is a chi-square distribution, and I think, so I want a 95%. Okay, so what we're going to do here, we're going to go n minus 1 times my variance over chi-squared right less than variance squared less than n minus 1 variance chi-squared left. Why am I doing that? I'm wrong. We're doing differences. I'm sorry. I apologize. We're doing differences, so it's x bar minus y bar minus e is less than mu1 minus mu2 less than x bar minus y bar plus e. Okay. Chi-squared was that question we did before class. I was just in that mode, sorry. So then E, so we got to figure out what E is. Okay. E, if you remember from yesterday, okay, it's your Z sub alpha over 2, okay, and that's attached to the 95% that we're looking for, okay. So that's 1.96, right? Okay. Then we're going to find our standard error, which in a difference of means situation, your standard error is found by taking the variance of one population divided by its sample size, plus then the variance of your second population divided by its sample size. Okay. So E is going to be 1.96. That's the Z score for 95%. Okay. Now, do they give me sigma throughout this situation for one of my populations? Yeah. Okay. They give me 1.9. So I'm going to go 1.9 squared. Okay. And now in that 1.9, so it's how many? So 1.9 is the standard deviation for the population. M is the sample size out of that population. So that was 167 reports. Does that make sense? So 167 there. And now just find the same information about the second population. The second population would have been after the fires. So we've got 125 of those reports. And the standard deviation is 2.3. Is that okay with everybody? Okay. Now I've also got to find x bar minus y bar. Okay. Well, X bar minus Y bar, that's the sample means. That's the difference in the sample means. Okay? Well, one of those samples, the first one, was 5.2. That was the sample mean. Does that make sense? So X bar minus Y bar is going to be 5.2 minus then the 6.8, which is the other sample mean. Is that all right? Okay. So now, if we go ahead and compute those things, go 1 point, so I'm going to say E is equal to 1.96 times the square root of 1.9 squared over 167 plus then 2.3 squared divided by 125. Here's my margin of error. Okay. Now I want X bar minus Y bar. So I'm just going to call this M for mean. I wish I could say, like, they won't let me use two letters to abbreviate things or to define variables. So I'll use M here. So 5.2 minus 6.8. Okay. So now if I want to find X bar minus Y bar minus my error, it's going to be M minus E on Desmos here, right? So we get negative 2.095. Okay. If I go M plus my error, it gives me negative 1.10. Okay. And you can see here in the notes I've already got those values kind of typed through. But now it says negative 2 less than mu1 minus mu2 less than negative 1, right? So what does mu1 minus mu2 have to be? What kind of number? Mu1 minus mu2 has to be a negative number. So mu1 is going to be less than mu2, right? Mu1 was the average of the population, the mean of the population before the fires. This is after the fires. So were the biologists right that because of the fires, fishing got better? Does that kind of make sense to everybody? And now we're not just saying, here is one number, the average catch per day, and making a justification off of that one number. Okay? We're looking at 167 samples, 125 samples, or 167 situations and 125 situations. Okay? Does this kind of make sense? All right. That is, so us getting to that point of saying like mu1 is less than mu2, that is very close or closely related, and almost just like a parallel track in regards to what we call hypothesis testing. Okay. Because eventually, when we do all of this stuff, that's what we want to be able to do. Can we, a biologist made a claim, can we accept that claim or not? Okay, and that's what hypothesis testing will let us do next week. Okay, I will post, so that there's, like I said, there's a question or an assignment with 5 questions, 6 questions in Math Excel. Right now I've got that closed off at Thursday night. The review for this chapter, I will get that posted here within the next couple hours. And like I said, I'll try to keep that as closely related to the actual test, but it'll be lengthier. Okay. As you're going through that, make sure that you pay attention. Like if you struggle, actually, I'll have to write this. I will send you out an email because if you look into Math Excel, I don't know if I've got any of it. Okay, you see how it says 6.4? Okay, we're not in 6.4, right? We're in 8.4. Okay, so the textbook that I'm taking these questions from does not align with the textbook that the notes are based off of. Does that make sense? So I will send you out a chart that will allow you to maybe connect the dots on what sections to look at if you're struggling on those questions.